if the cross-sectional area is less and I'm pulling on it, the stress on this side is going to be higher than the stress on that side. True? So it looks like that we would pull this material in two before we'd ever pull that material through the die. But the fact of the matter is, we can do that if the draft or the reduction in going through that die is too great. So we have to, for the material that we're looking at the temperature we're going to work it at, within the period of time that the material will relieve the strain that you put in it, and there is such a period of time, that is to say, when I pull it hot, I'm going to cause it to become harder for just a very brief period of time, and then it's going to recrystallize, it's going to reform, it's going to relieve the stresses, it's going to reconstitute its stress. So there's a time factor that goes in this, but there's a draft factor that allows us to pull the material through hot. Now, we could also make a tube like this, and all we'd have to do to have a tube is to start with a tube that may be a hollow section that's going to go in here, but it would have to have been produced before we ever got to this stage by piercing a billet or making a hole through a solid piece. Let's presume we can do that, and I'll tell you in a moment how you could do that. Then what we do is we start it through a die, and we put a mandrel inside of the die, or we just put let's say a little post inside of the die, so that the tube cannot close down as it's going through the hole. So there's a little solid piece of material that fits in here, and we pull on this end, and it falls down and collapses around that tube, and we make a smaller piece. Now we may have to do this time and time and time again. So in fact, if you look at something that's a stainless steel hollow tube, and I'm sure you have looked at many one of those and squeamishly when they were ready to give you a hypodermic, right? That little stainless steel tube had to be made somehow, and the way they made it was they started off with a stainless steel billet that they pierced or made it as a seamless tube. I don't know whether you've ever played with Play-Doh or not, or plasticine, or whether you make biscuits or play with real dough or not. But if you do, you will understand what I'm talking about. If you take some Play-Doh or plasticine in your hands as a big ball and you begin to roll it, and then you're going to roll it up into a long section, you will have noticed that if you squeeze it too hard as you're rolling it, then it splits right in the middle because you're shearing one side relative to the other side in an opposite direction. And so you have a shear stress in the center that just splits it open. Well, if you took a steel or a metallic material and you did the same thing, that is you rolled it in opposite directions and put a lot of pressure on it at that time, it would split right in the middle. It would open up a tiny hole. So if at that instant you had a pencil, let's say a mandrel or a tool that would pierce that little teeny crack, it would go all the way down the material and expand it. And that's the way they make a seamless tube. How do they get that shearing stress? They put it through something called Mannesmann rolls. And the Mannesmann rolls, instead of being two rolls that sit one over top of the other like that, they're crossed a little bit like this, and they run the tube through the middle, and it puts that shearing action in the billet to open it up to make the pierced tube. And then what they do is they take that tube and they have to start it in the die. So they have to point the end of it, and they point it like a pencil, and they have a machine that does that so that you can stick it through a little bit and then grab it and pull it. And they pull it down from a big billet to a fine tube that you call hypodermic needles. And they just keep on redrawing and redrawing and redrawing. Now, you do some of this hot and you do some of this cold, and you have problems because if you do it cold and you work hard in the material, finally you put all of that modulus of toughness, all of that energy in it, the material will stand, and you couldn't draw it again without breaking it. You have to put it back in the furnace and anneal it, reconstitute it, make it soft again, and then you can start to draw it again. So we have then that particular method of doing working, and we also have another method that I thought I'd best tell you about, since I just told you how to do chill block melt spinning. Now that was when we made that continuous casting. That's what it's called today, chill block melt spinning. But the word spinning has been around in the metal industry, has been around much longer than this casting technique of spinning. And spinning is an operation that's used to make complex symmetrical parts, like, wine glasses if you want, or horns for public speaking systems and the like. And the setup is something like this. All you really have to do is have a lathe, let's say, that will rotate a piece of work. And this is the piece of work that we are going to consider. Actually, that piece of work started back here, which was a block that held a great big circular plate against a mandrel. This is the mandrel in the back. And we're going to try to make a conical section here. So the operator has to have a tool rest, just like he would have if he were, say, machining a piece of material. And he brings it to bear on the material at this particular point, rotates the lathe very rapidly, and then he follows it with this stylus or this tool, the spinning tool. This is called friction spinning. Actually, the material heats up a bit because of the friction there, but he really can do this hot, and he can follow it along, and he can make any shape he wants that's symmetrical. Well, that is going to score the surface of the material, and we don't use that for very, very large and complex shapes. We use something that's called a roll spinner, and it looks very similar to that. And this is a rolling type spinner. And now here is the tool block. This is the piece of material that we're going to ram against the mandrel. The mandrel is this piece in the back. And we eventually going to turn a workpiece, which was just a cylindrical, a circular plate, like a record that sits up here. And we are going to turn it into the shape that's just exactly the shape of that mandrel. So the operator puts that piece of circular material in. He advances this piece of tailstock until he pinches it in so it can't go anywhere, turns his lathe on, it's rotating rapidly, and he takes this tool, which again is on his tool rest, and he forces it against his side, and he moves it from position to position. And this shows it in two different positions, and he rolls the material, and it will conform, come out, be a beautiful copy of that workpiece. If you did this with a roller that looked like this, so we have a roller on either side to do a complex piece, you can make very deep weld pieces. And in fact, all the ends of tanks that you know, flanged heads. If you look at a tank, let's say a tank on the end of a truck that has elliptical section or spherical section. Many of our tanks are this way. We need them to be that way because of the pressure containment. And you'll find that it has a flanged edge, and then they're welded. The flanged edge is welded into a cylindrical plate. Well, how in the world do they make that thing? They make it in a flanging mill, and they heat up a great big circle of steel. They have to have cut the circle out. They take it out of the furnace, and it's sort of flimsy like a piece of rubber. It's plastic. They sit it on top of this tool, this mandrel, which is the shape of the inside of the piece they want to make. And they start at the top with this rolling tool, and they roll it around the edge and roll it down the side, and they just shape this thing in a hot form. And the edge may be slightly ragged around the outside. That can be machined off smooth. But a man does this by eye. Of course, he has instruments that he can measure. But if you imagine somebody starting out with, say, a 150-inch circular section, and he wants to roll that into a flange, he's going to have some measuring tools that are rather unique. And I've watched these guys do it, and they're just artists, and they control that roller on the side with some electrical controls, and then bring the roller around, roll the flange on it, and just do it almost perfectly. When he brings his ruler out to measure it, he rarely ever does anything else. He'll just take it off and ship it. So it's a hot working technique that's used a lot in the field.
Various types of hot rolling mills can be used to produce billets, rounds, squares, and sheet metal. These include three-high mills, tandem mills, and matched roll mills. To stamp or forge a metal product, molten metal is compressed between an upper and lower die. This hot working method is often used for piecework. Extrusion requires high pressure, so container walls must be able to withstand the pressure of the molten metal within. To successfully pull material through a die, as in wire drawing, one must ensure that the reduction is not too great, because high reductions cause the material to be pulled apart. Spinning is a hot working method that is often used to make electrical parts. A lathe rotates the workpiece, while a tool shapes the material over a mandrel.
if I can now, I'd like to walk back and come through the steel mill for you, and I want to tell you how to make two things, and it involves some steps, some metallurgical steps that we haven't talked about, and they will become important to us later on when we talk about corrosion. But let's suppose that we have made the ingot of some kind, and we now want to produce a product, and let's suppose we want to produce billets. We can produce the billets very easily by just going through one of these matched roll techniques and keep on making this big square ingot that we had, smaller and smaller and smaller, but we'll keep it square until the last set of matched rolls will change it from a square to a round section. So we come up with, say, round rods. Those round rods we will take to a wire drawing station, and we'll draw the wire down, hot or cold, till it's smaller and smaller and smaller and smaller. And when we finally get it as small as we want it, then we say, all right, I want to make a product now. I want to put this in the final form. But up front there somewhere, when we're pulling it through the die, we may have damaged the die. Why? Because if it's iron, steel, then it scales. You have it hot. If it's hot rolling, it develops an iron oxide scale. That's a brittle, tough, abrasive material, and it would scratch the die all up. So we want to get it off. So we do something called pickling. You connote pickling. Do you know what pickling, the word pickle means? What does to pickle mean? You ever get pickled? Pickling actually means to treat with acid. You know, when you make pickles, you put them in acetic acid and vinegar, right? And we pickle the steel. We put it in sulfuric acid, like 10% sulfuric acid at 150 degrees, and it blows the scale off. Blows the scale off. Because the hydrogen is small enough to squirt into the crystal lattice, if it's atomic hydrogen, and it moves around, and some of it comes back out and combines with another atom of hydrogen, makes a molecule of hydrogen that's bigger, and it blows the scale off. And so we keep the scale clean and off of the material, and we can draw it through and continue to get a product. So we have to clean it by pickling frequently in the steel mill. But now we have a nice clean rod of wire, and let's suppose we are interested in making a 6-penny nail, and that we have drawn it down to the size, the diameter required for a 6-penny nail. We put it in the nail room, and it's just a coil of wire. It goes into a machine, it runs into the machine, and it's grabbed two ways. It's grabbed up front, and it's grabbed so tight that a little piece of this wire extends beyond the die itself, and there's a hammer that comes in and slams into the top of it, and that's called heading, and it heads the nail up, right? The other end, at the exact same moment, is gripped by a pair of cutters, and they come in and they cut the end off of the nail, except when they do it, they slice it off perfectly square on one end and cut 4 little quadrants off of it, and that's the point of the nail. And there's a byproduct, and that's nail whiskers. They're all those little pieces that come off, and we use in ball mills and tumbling mills to clean material with. And then the next piece of wire is advanced, it's grabbed again, and it slams, and the thing I've just described to you goes like, and you have lots of nail mills in one room, and everybody who works in a nail mill is deaf. Always seems so to me. Well, we can follow almost any product through the steel mill, and we find out that basically now we have covered the steps. We're going to hot form it, we're going to roll it, we're going to draw it, we're going to pierce it, we're going to fabricate it by rolling or drawing or extruding, and finally we get our final product. Now there's one product that I hadn't talked about that we'll talk about this afternoon when we talk about joining, because there's some operations in the steel mill that are continuous that have to do with welding. Well, we still have to look at forming the material or getting it into a usable form by doing cold working, and so we'll do that in the next lecture. Thank you.